everyone. This channel is talking about bulk materials. Today's video number 4. Today's topics equation of wall thickness calculation for pressure retaining parts. We will discuss about the requirement of minimum wall thickness for bulk body in ASME B16.34. Here, assign the description of the related wall thickness taken from ASME B16.34. So, paragraph 6.1.1, wall thickness. For inspection purpose, the wall thickness of bulk bodies at the time of manufacture shall be no less than the minimum values Tm, either as shown in Table 3a or Table 3b, or calculated using the equation shown in mandatory Appendix 6, which yield essentially the same result. The minimum thickness requirement for the body wall is applicable only as measured from internal wetted surface. Paragraph 6.1.2, inside diameter. For the purpose of determining wall thickness Tm using Table 3a or Table 3b or the equation in mandatory Appendix 6, the inside diameter d shall be in accordance with the following requirement. The inside diameter d shall be the minimum diameter of the flow passage, but not less than 90% of the basic inside diameter at the valve end. So here indicated the Table 3a for valve body minimum wall thickness table. So unit the millimeter. So Table 3b is indicated the unit to inch unit. So Table 3a is the left side column indicated the inside diameter d, millimeter. So 3 millimeter, 6 millimeter, 9 millimeter, 12, 50 millimeter. So indicated the stepwise indicated the inside diameter. So horizontal line indicated the rating class number, class 150, 300, 600, 900, 1500, 2500, 4500. So inside the number value is indicated the minimum wall thickness values. For example, 40 inside diameter, 40 millimeter, and rating class 600. So 5.6 millimeter is indicated for minimum wall thickness values, 5.6. The wall thickness of bulk bodies was designed and manufactured by ASME B16.34 shall be no less than the minimum value Tm, as shown in Table 3a or Table 3b. Table 3a shown in right side, which is derived from ASME B16.34, is for SI unit. For the purpose of determining wall thickness Tm using Table 3a, inside diameter d shall be the minimum diameter of the flow passage, but not less than 90% of the basic inside diameter at the valve end. So this figure is indicated the valve body for flange end valve. So this area is the flow passage. So inside diameter D is at the bulb end. Bulb end inside diameter D measured and obtained here. So the casting body material received from the casting supplier, receiving inspection shall be conducted by the receiving inspector. He conducted the measure the first inside diameter D at the bulb end point and measure the inside diameter. For example, 50 millimeter inside diameter measured. So the questioned bulb body's rating class is 600. So 50 inside diameter D and class 600. So 6.2 millimeter minimum wall thickness requirement. So inspector measure the bulb body wall thickness with something caliper. So any area, any location is measuring the with the caliper measured wall thickness. And all measured thickness values to be larger than 6.2 millimeter. If the measured wall thickness is larger than 6.2, that bulb body is passed. Okay, so measured wall thickness shall be no less than Tm of minimum wall thickness obtained from Table 3A, Table 3B, or Appendix 6. So minimum wall thickness requirement is for inspection purpose in the ASME B16.34 requirement. This table 6 is for equation. Minimum wall thickness TM calculated using the equation in mandatory appendix 6. So 6-1 minimum wall thickness equations. Minimum wall thickness requirement may be satisfied by compliance with either the values shown in Table 3A or Table 3B as applicable, or the use of the equations listed in this appendix. So design values. The wall thickness values obtained from Table 3A, Table 3B, or the equations given in this appendix are not to be interpreted as design values. They are, in basic terms, minimum requirements that must be met in order to be in conformance with this standard. So indicated table 6-1 basic equation for minimum wall thickness unit millimeter. Table 6-2 is a unit inch unit. So this left side column there indicated the rating class number, and inside diameter D, and the metric equation Tm equal something. So round off 1 decimal. So here table A1 indicates the relationship, the NPS size and the inside diameter D for each rating class. Table A1 established between nominal pipe size and the inside diameter of fittings, matching the rating class of the flanges. This provided a useful design basis for the corresponding flanged end valves and weld end valves. So table A1, so left side indicated the NPS size. 3 inch, NPS 3, 4, 5, 6, something. So horizontal line, the class number, class 150, 300, 600, 900, 1500, 2500. So table A1 indicated both unit, millimeter and inch. Both unit is very convenient tables. In case of the NPS 3, class 300, in case of the class 300, so inside diameter D equal 76.2 millimeter requirement. So table A1 is based on the dimensions given in ASME B16.5 dimensional tables as the inside diameter of fittings. Table A1 taken from the ASME B16.34 valve standard. B16.5 for flange standard. So flange standard and valve standard is the same inside the table, inside diameter table to be used. So the inside diameter between the valve side and the front side, it to be matching is very, very important. So next is we try to find the required minimum thickness by the inside diameter of the valve body. So assume the valve size NPS 3 class 300 and base the face of the flange and valve. So NPS 3 and rating class 300 we refer to the table A1 and NPS 3 and rating class 300 we catch the inside diameter 76.2 millimeter. So inside diameter 76.2 millimeter from table A1. So required minimum thickness refer to the table 3A here, millimeter. So inside diameter 76.2 millimeter, not shown here, tabulated number not shown. So we have to the minimum thickness calculated by the interpolation method. So 300, 6.9 and 7.0. This is between the calculated wall thickness by the interpolation method. So rewriting the table 3A, inside diameter 75 millimeter, 80 millimeter. This is tabulated number. So 76.2. So class 300. So calculate the wall thickness 6.924 with the interpolation method. We obtained the 6.924 millimeter obtained. So another equation we can be used the equation table 6.1. If we using the equation of table 6-1, this is in mandatory appendix 6. So this is table 6-1. So that translating 300 and diameter D equal 76.2 millimeter. So here this line. So Tm equal 0.033 multiply D plus 4.40. So round off 1 decimal. So this equation to be used. So Tm equal 0.033 D plus 4.40. So substitute 76.2 into D. So calculate Tm equal 6.9146 millimeter. So round off 6.9146 to 1 decimal. So Tm equal 6.9 millimeter obtained. Next, we will discuss about the equation B1 of wall thickness for bulk body in ASME B16.34. Here is assigned the description of the related wall thickness equation taken from Appendix B. Appendix B is a non-mandatory Appendix B in ASME B16.34. So it is not required that indicated materials be used for bulk body and bonnet or bulk body and cover. However, both shall be from materials listed in table 1. So table 1 is I talked about table 1. This is a material listed in ASME B16.34. Many materials assigned the table 1. The previous video is number 4 I talked about. The assigned pressure rating shall be based on the bulk body. The bonnet or cover shall be designed and material subject selected accordingly. So again, this sentence is again repeated. The materials of bulk body and bonnet shall be used from material listed in table 1. But the pressure rating class and wall thickness requirement shall be applied on the only bulk body, not applied the bonnet. The wall thickness area. Wall thickness requirement for bulk bodies are specified in paragraph 6.1. The minimum wall thickness values Tm shown in table 3a or table 3b calculated using the applicable equation of mandatory appendix 6 are all greater than those determined by the following equation. Following equation here, equation B1 is not to be used for design calculation and is not to be used as a substitute for either Table 3A or Table 3B values or mandatory Appendix 6. So, equation B1 for wall thickness calculation equation, but this is only for purpose of the general interest. Do not use for the design calculation or not to be used as a inspection purpose. This is the interest, general purpose only, general interest only, this equation. So T is a calculated thickness, and 1.5. 1.5 is meaning the factor 1.5 times. So that term in the parentheses is this is basically the wall thickness calculation terms. So B, the inside diameter. PC is a pressure cross designation number. For class 150, PC equal 150, or class 300, PC equal 300. So SF, pressure stress-based constant equal to 7,000. SF is mean equal constant number 7,000. So additional consideration. In the equation B1, result in wall thickness of 50% greater for class 150 to 2500 and approximately 35% greater for class 4500 than for a simple cylinder designed for a stress of 7,000 psi subjected to an internal pressure equal to the pressure rating class designation PC. So the order of the simple cylinder design, I think here it is supposed that the following equation is for a simple cylinder designed. Here, this is a simple cylinder designed equation. That equation is very popular, the thickness calculation in the pressure retaining parts, such as ASME Section 8 Division 1 pressure bezel standard or ASME B31.1 per piping standard. This is a typical wall thickness equation for the several standard. TP equal wall thickness, D is the inside diameter, P equal internal pressure, sigma equal stress occurring during interest pressure applied. So that the term, the parentheses, almost same forms. This one. So the following term, this one. So the term in the parentheses move to the here, dividing in the here. So assign the T dash equal PCD bar and denominator here. So the following term in the equation B1 is equivalent to the equation of the simple design cylinder designed here. equivalent to the equation of the simple designed cylinder designed. So PC equal pressure class designation number for internal pressure. SF equal 7,000 psi for stress occurring during internal pressure. So here commented this 7 stress or 7,000 psi. And subject to the internal pressure equal to the pressure rating class PC. So it is understood that 1.5 times of the equation B1 means a wall thickness of 50% greater than for a simple cylinder designed. T equal 1.5 times T dash. So easily understanding the this means wall thickness 50% greater than a simple cylinder design. So, but however, a question remains about the sentence that express approximately 35% greater for class 4500. So here, this sentence, approximately 35% greater for class 4500 than for a simple cylinder design. This is a question remained. I will talk about this matters later. So again, I assign the B1 equation here. So TB equal 1.5 much times something. So we calculate variable thickness inside diameter. PC is a rating class designation number. SF storage based constant equal to 7,000. ASME B16.34 comments that the calculated minimum wall thickness values by equation B1 are less than the values taken from table 3A or table 3B or the calculated values in appendix 6. Table 3A, table 3B, and appendix 6 are to be corrected for using actual valve wall thickness inspection. On the other hand, the wall thickness values calculated by B1 are always bigger than the calculated thickness by simple thin-walled cylinder model, such as the equation of piping component, as can be seen from 1.5 times in the equation of B1. The equation of pipe wall thickness calculation by ASME B31.1 is as follows. So that ASME B31.1 is a power piping standard. So the wall thickness equation is basically the outside diameter basic equation constructed. Outside diameter zero base. So compare with the B1 equation, so that converting to the inside diameter d based. So TP equal P multiply d, small d. Small d is the inside diameter. and dominated term is like this. So, changing the y factor y minus minus 1 is changing. So where DO outside diameter, small d inside diameter, E is a welding joint efficiency. But in case of the consideration, welding pipe is not assigned. So casting pipe assigned. So E equal 1.0 to be considered. And casting factor, we will consider about the casting pipe. So we take care of the casting factor, casting quality factor, F. So in case of the casting pipe, F equal 1.0 to be considered. W is the welding strength reduction factor. So there is no welding line. So W equal 1.0. So discussion this equation for ambient temperature level. So y equal 0.4. So y number, y factor is for below 900 Fahrenheit, always y equal 0.4. So ambient temperature also y equal 0.4. So arranging the equation like this, it's very simple here. So 0.4 minus 0.6. So multiply 2. So minus 1.2 multiply P. Okay. So S stress subject by internal pressure. So P internal pressure of maximum working pressure. So here, I wondered before, what was the significance that PC indicated rating class designation number for the internal pressure, and SF indicated 7,000 stress constant for allowable stress in the wall thickness equation B1. And also, same question arose on the equation B4 of establishment for the allowable working pressure on the special rating class in ASME B16.34. So I talked about allowable working pressure established method for allowable working pressure in the previous video number 3. So I again assigned this in the description. Method for pressure temperature rating in ASME B16.34. This equation for a standard class working pressure obtained equation. PST is the standard class rated working pressure. And here is a special class. PSP is a special class rated working pressure. So that equation, the denominator number 8,750, and This is a very unique number assigned. Also PR. PR is not pressure, actual pressure. Pressure class rating index, rating class. 300, 600 rating class indicate. I wonder that why as the denominator 8750 and the PR indicated the rating class number. So also the special class denominator 7000 constant number assigned. PR is a rating class number assigned. This is very I wonder that why the reason why assign the 7000 and the PR equal the rating class number. So what is the significance of PR, rating class designation number, and 7000 of denominator in the equation B4? So we will discuss later about those to understand the establishing of the wall thickness and the rated working pressure in ASME B16.34. Now we talk about the relation between PC of pressure rating class number and P of internal pressure. Comparison between the variable thickness equation based on the simple thin-walled cylinder model. T dash equal PC multiply B divided by the terms of the in the parentheses derived from B1 for body body. This for 1.5 times this in the terms of the parentheses. This equation is assigned the T dash. So this equation is for actually wall thickness calculation equation. So and the pipe component wall thickness equation based on the simple thin-walled cylinder model. Tp equal P multiplied by B divided by the denominator like this for piping component. This is basically the piping component for the ASME B31.1 equation. That equation is outside diameter dO based. So convert to inside diameter small d base and simplify the equation like this based on the inside diameter d based. This is Tp. So Tp equation we assign the number 2. SF the 7000 stress constant phasors S stress subjected by internal pressure, normally consideration of the allowable stress. PC rating class designation number phasors P. Internal pressure, normally consideration of the design pressure. It is understood that S over stress means allowable stress which is normally indicated by tensile strength multiplied to 25%. Allowable stress is usually derived from either of tensile strength multiplied 1/4 or yield strength multiplied 2/3, whichever is lower. In case of ambient temperature, tensile strength multiplied 1/4, 25%, is always lower than yield strength multiplied 2/3, and selected for allowable stress, as shown 3 in the attached table for 1 to 1. This table is for 1 to 1. This table for barrel materials, so the material strength level. So barrel material has a soft material, not hardened. So almost unmoved condition. So for ferritic steel, roller steel, and carbon steel. So that ferritic steel indicated yield ratio almost cover the 50% to 60%. And 40% for almost austenitic stainless steel, and sometimes nickel alloy. So I think the all barrel materials cover the yield ratio 40% to 60% range. So tensile strength indicated 1.0 indicate. So that the yield ratio 40%, yield strength 0.4 indicated. So yield ratio 50%, yield strength 0.5 indicated. So yield strength of 60%, yield strength 0.6 indicated. So number 3 here, allowable stress establish factor. All standard for pressure retaining parts assign the allowable stress factor, the two factor, tensile strength and yield strength. Tensile strength is multiply 1/4, 25%, and yield strength multiply 2/3. So nowadays the almost standard assign the safety factor of the tensile strength around 3.5, 0.285 assign the safety factor. So safety factor 1/4 is used before. So the number 3 here. This method for establishment of allowable stress had been formally used before 1998 in ASME Section 2 Part D. So before ASME assigned the safety factor of the tensile strength 1/4, 25%, but nowadays the 0.285 is assigned there for safety factor. But ASME B16.34 is a very old standard establishment around 70 or 80 years ago. At that time, so ASME Section 2 Part D assigns the allowable stress establishment factor is a tensile strength multiply 1/4 assigned. So I also assign the here 25% safety factor for tensile strength. So tensile strength 1.0, so 0.25. Tensile strength levels indicated 0.25. All three yield ratio 0.25. How about the yield strength? Yield strength 0.4 multiply 2/3. We obtain the 0.267 and yield strength 0.5 multiply 2/3 0.333. 2/3 equal 0.666, so around half 0.333, and yield strength 0.6 multiply 2/3 0.400. So tensile strength multiply 1/4 is 0.25 is still lower value than yield strength. So at the ambient temperature, the tensile strength multiply 0.25 is selected for allowable stress. The tensile strength multiply 0.25 is lower than yield strength multiply 2/3. Tensile strength multiply 0.25 is usually selected to allowable stress at ambient temperature. So if the tensile strength 70,000 psi of WCB casting is considered as the basic strength in ASME B16.34, we have S allowable stress equal 70,000 psi multiply 0.25. Assuming that the calculated thickness of T dash and TP both have the same value if SF is 7,000 on the equation 1 and SE is 70,000 multiply 0.25 on the equation 2, we will find the relation between PC and P. The equation number 1 equal the equation number 2. So alignment to the equation like this. So both terms D deleted, and denominator term moved to the left side. Also denominator moved to the right side, and align the equation like this. And 1.2 multiply P multiply PC here, and also 1.2 multiply the PC multiply P like this. So the like terms deleted these terms. So we simplify the equation like this, and we have like this relationship P and PC, P equal 2.5 multiply PC. We have obtained. P of internal pressure is 2.5 times as large as PC of the pressure rating class number. Actually, substituting class 150, class 300, class 600, 900, 1500, 2500, and 4500 into PC, we obtain the value of the P as P equal 375 psi, 750 psi, 1500 psi, 2250 psi, 3750 psi, 6250 psi, 11250 psi, respectively. It is obvious that these values of P are equivalent to cold working pressure of maximum working pressure of PCB of ceiling pressure in table B3C. As shown A in the attached table 41212. So again, I assign the ceiling pressure in table B3C. I talk about that ceiling pressure in the previous video number 3 in some detail talking about this. Now assigned here. So table B3C ceiling pressure, so A is the standard class and B is the special class. So temperature and the rating class. So this indicated number for maximum working pressure. So limited working pressure indicated. So that ambient temperature is we called cold working pressure. Cold working pressure is the most highest working pressure indicated. So if we use the relatively stronger material used for bulk material, calculated the working pressure, allowable working pressure. So the big number for the obtain the higher value of the working pressure, but ceiling pressure is limited to the value of this. So that indicated number is the maximum limited number values indicated. This is for ceiling pressure. So cold working pressure for ceiling pressure is for standard class and also special class. The same value indicated. So table 1422 table. So relation between PC and CWP of ceiling pressure. So PC, pressure rating class number, 150, 300, 600, 900, 1500, 2500, 4500. And cold working pressure, ceiling pressure is indicated table B3C. Write down here to 290, 750, 1500 like this. So write down cold working pressure with ceiling pressure. So pressure rating class number 150, but I assigned the 115 number. So by paragraph B 2.3 and paragraph B3 of appendix B in ASME B16.34 commented. So method of the pressure temperature rating in ASME B16.3. This method uh, I talked about previous number 3 video very detailed. So now I'll reassign this description. So this equation for PST, standard class rated working pressure. Working pressure rating class is equation for standard class. Right side, PSP equal special class rated working pressure. Like this equation for working pressure for equation for special class. So B-2.3 method for class 150. The value of PR equal pressure class rating index. The pressure class rating index for class 150 shall be 115. So this comment, I assign the 115 for class 150. So the value of PST, standard class rated working pressure, for class 150 shall not exceed values at temperature T as given by equation B3. So this is equal for cold working pressure for sealing pressure. So C2 equals 320 and C3 equals 0.3 with T expressed in Fahrenheit. The resultant PST will be in PSI unit. So that if PST will be in PSI unit and T in Fahrenheit, PST less than 320 minus 0.3 multiply 100 Fahrenheit. So PST less than the 290. 290 is the cold working pressure of the sealing pressure at the rating class 150. So also a special class for class 150, PR equal 115. So this comment is for I assign the 115 pressure rating class index number. So the ratio of the CWP PC is 290 divided by 115, the 2.5 obtained. 750 divided by 300, 2.5 obtained, the ratio. So we obtain the 2.5 ratio here. So it is obvious that these values of P are equivalent to cold working pressure of maximum working pressure PCB of sealing pressure in table B3C as shown A in the attached table for 1, 2, 1, 2. The Next, we talk about the relation between SF and S will be found as using of the relation of P equal 2.5 multiplied by PC. Equation 1 equal equation 2, so arranging this equation. So substitute 2.5 multiply PC into P. So deleted the PC and move to the denominator left side and move to the right side. So arranging the equation here and like term deleted here. So simplify the equation. So S equal 2.5 multiply SF is obtained. So S and SF relationships obtained. It is understood that SF equal constant 7,000 multiply 2.5 equal 17,500 psi equals to S the allowable stress. So 70,000 of tensile strength multiply 0.25 equal 17,500 psi. So S equal something equal good relation. So I am confident that the tensile strength 70,000 psi of WCB casting is considered as the basic strength in ASME B16.34. Next, we talk about the relationship between PSP of special class rated working pressure and PR of rating class designation number in the equation B4. So write down the equation B4. Again, here this is a B4 equation for a special class. So equation for working pressure like this. So PSP is special class rated working pressure, and PR rating class designation number class 300, class 600, like this. PCB is a saving pressure. S2 is a selected stress. C2 is a coefficient equal 1 if S2 will be in PSI units. Substitute 1 into C2 like this equation, and if the tensile strength of WCB casting is considered as the basic strength in ASME B16.34, we have S2 equal 70,000 multiply 0.25 as shown number 2 in the attached table 14114. 4121. Okay, S2 selected stress for the special material at temperature T, psi. The value of S2 shall be established as follows. At temperature below the creep strength, S2 shall be equal to or less than 62.5% of the yield strength at temperature T, but shall not exceed number 1, 62.5% of the specified minimum yield strength at ambient temperature. Number 2, 25% of the ultimate tensile stress value at temperature T. So, table 4.1 So selected stress S2 established factors for special class. So two factors are assigned. Tensile strength multiply 25% or yield strength multiply 0.625 whichever is lower value is selected for selected stress S2. So yield ratio 40%, 50%, 60%. So tensile strength multiply 0.25, 0.25 like this. So yield strength 0.4 multiply 0.625 obtain the 0.25. 0.5 multiply 0.625 obtained 0.313. 0.6 multiply 0.625 obtained 0.375. So tensile strength multiply 25% is lower than yield strength. So tensile strength multiply 0.25 is lower than yield strength multiply 0.625. Tensile strength multiply 0.25 is usually selected to S2 at ambient temperature. So we have S2 equal 70,000 multiply 0.25 as shown number 2 in the attached table for 121. PSP equal 70,000 multiply 0.25 divided by 7,000 multiply P by PR. So we obtain the PSP equal 2.5 multiply PR. Because the maximum working pressure PSP is equal to cold working pressure of PCB of the sealing pressure in table B3C. PSP equal CWP for special class equals 2.5 times of rating class number PR. So next we talk about to confirm that obtained minimum wall thickness TM in table 3B are larger than the addition of 0.1 inch and calculate equation B1. The attached table 4131 shows that the obtained TM in table 3B is larger than TV plus 0.1. In case of inside diameter 3 inch and 6 inch, TM equal TV plus 0.1 are recognized in rating class 900 or more. This table is tabulated, summarized calculation. So compare calculated thickness TV plus 0.1 inch with TM in table 3B. So Left side indicates the pressure class rating index 150 for 150, 115 indicated 300, 600, 900, 1500, 2500, 4500. For this inside diameter assigned 3 inch here, and also 6 inch here, and same pressure rating class number indicated here. So number 2 is B1 equation, the valve wall thickness calculation equation. So PC and D substituted by the PC and this number inside diameter inside here. So we obtain the TV equal 0.037, 0.99, like this number obtained. So TV plus 0.1. So ASME says TV plus 0.1 is something saying. So again, here the equation of the wall thickness subscript, but the actual values in table 3A or table 3B are approximately 0.1 inch larger than those given by the equation. 0.1 inch larger. So ASME commenting like this. So TB plus 0.1, we obtain this number here. So compare the TM, required minimum thickness from table 3B. From table 3B again, I assigned table 3B, body minimum wall thickness as an inch unit. So this rating class number, and inside diameter D is 3 inch, class 150, 0.24 inch minimum wall thickness, 300, 0.28, like this number. And inside diameter D, 6 inch, 0.38, like this number. So assign the rewriting the minimum wall thickness values here. So compare with the TB plus 0.1 and TM. So TM is larger than the TB plus 0.1 inch. So, but the 900 rating class over same value indicated 0.41. So 6 inch also 900 rating class over same thickness values indicated. Anyway, tabulated wall thickness value Tm is larger than the calculated wall thickness. So in case of inside diameter 3 inch and 6 inch, Tm equal Tv plus 0.1 inch are recognized in rating class 900 or more. Next, to compare the calculated wall thickness Tb by the equation B1 with the calculated wall thickness Tp by the simple thin-walled cylinder and TL by the Lamé stress equation. The attached table 4131 shows that the calculated wall thickness value of Tv by the equation B1 are 1.5 times as large as the calculated wall thickness value of Tp by the equation of the pipe component wall thickness, except for class 4500. So again, this equation for calculation of the piping component wall thickness calculation. So P inlet internal pressure P equal cold working pressure over sailing pressure in table B3C, and stress is allowable stress 70,000 multiply 0.25 for WCB casting tensile strength, and safety factor 1/4. So 70,000 multiply 0.5. And P is CWP like this. So calculate wall thickness Tp is obtained like this. So compare the for variable wall thickness Tv, calculated number Tv and Tp, compare the rate number 2 bar, number 3. So number 2 wall thickness is larger than number 3. So 1.49, 1.50, 1.50. So 1.5 times obtained. So because of the this equation is 1.5 times. So immediately we easily understood 1.5 times than Tp. But again, I remember that here, this note, the equation B1 here result in a wall thickness 50% greater for class 150 to 2500. This is correct. We understood. And this comment, approximately 35% greater for class 4500 than for a simple cylinder design, like this. So my comment, however, a question remains about the sentence that expressed approximately 35% greater for class 4500. So, simple thin-walled cylinder model calculation. 4500 class is 1.57 thickness obtained. But arranging the K equal d0 bar d, this is a wall thickness evaluation. So when K equal 1.5 or less, number 3 equation can be used. Number 3 equation for thin-walled, simple thin-walled cylinder model equation. So in case of the 4500 class, wall thickness is thicker wall thickness obtained. 2.05 equal K equal 2.05. This is wall thickness is very thick wall thickness. So we cannot use this simple thin wall thickness equation. So we have to use the Lamé equations. So calculate thickness by Lamé's equation, like this. This equation shall be used for the thicker wall thickness cylinder model. So obtain the thickness calculation by the Lamé's equation, like this. So that number 2 by number 4, the ratio, the 1.49, like this, same as 1.5, but something different. So in case of the 4500 class, we obtain the thickness 1.717 thickness for 3 inside diameter 3 inch. Inside diameter 6 inch 3.434. So the ratio of the number 2 by number 4, 1.37, almost very close to the 35% larger 35% than piping wall thickness values. So since the equation of the pipe wall thickness calculation is based on the simple thin-walled cylinder model, this equation cannot be applied in case of thick-walled cylinder which has more than 1.5 of K equal d0 bar d, do outside diameter, small d inside diameter. It is indicated that the calculated wall thickness of TD for rating class 4500 is 1.37 times as large as the calculated wall thickness of TL by the Lamé stress equation. The wall thickness calculation for the piping component in the table 4131 is based on the assumption that casting quality factor is 1.0. Also, as seen just before, the maximum working pressure of the ceiling pressure CWP of special class in table B3C, which equals 2.5 times of the rating class number, is based on the assumption that 70,000 psi of tensile strength for WCB casting is basic maximum strength in the pressure temperature ratings in ASME B16.34. Both case of 1.0 of casting quality factor and the application of the special class. So 1.0 and the application of the special class, both cases require the appropriate ND test on the applicable materials. When 0.8 of casting quality factor is applied on the wall thickness calculation for the piping component, ND tests are not required on the casting pipe. And also, ND tests are not required on the applicable materials in case of applying of standard class valves. It is understood that the allowable working pressures in the standard class are almost 0.8 times less than that values of special class, as can be seen from that the denominator of the equation of B2 and B3 indicated 1 bar 8,750 and 1 bar 7,000 respectively. Again, we look at the equation of the working pressure equation. This standard class, denominator 8,750 indicated. And for a special class, the denominator 7,000. So 8,750 and 7,000, and the relationship rate is 0.8. So understanding that the required minimum wall thickness values of the valve bodies are determined by inside diameter D and rating class designation number. Factors of material strength are affected by the type of applied materials and temperature are not included in Table 3A, Table 3B, and equation of Appendix 6, and also in the equation of valve wall thickness calculation B1. Even though the actual strength of the assigned material, which are taking account of the temperature and safety factor, have been considered for the wall thickness calculation of such as piping components. The bodies of valves are designed and usually formed in the casting mold, which is produced with a fixed inside diameter and wall thickness. Therefore, it is important to determine the valve rating class with a corresponding rating table for each material group in ASME B16.34. So now we talk about summarizing about valve wall thickness. To summarize about the valve wall thickness and the pressure temperature rating class. So valve minimum wall thickness TM obtained in Table 3A, Table 3B, and equation of Appendix 6 shall be used for inspection purpose. And all these obtained minimum wall thickness TM are greater than the determined thickness TB by the equation B1 as TM larger than TB plus 0.1 inch. Additional 0.1 inch thickness is not intended use of corrosion allowance. Some guy is misunderstood. The additional 0.1 inch is a misunderstanding for corrosion allowance. This is not intended use of the corrosion allowance. Only additional thickness. Calculate wall thickness TV by the equation B1 is included as general interest. The equation B1 is not to be used for design calculation. Calculated wall thickness TV by the equation B1 is 1.5 times as large as the calculated thickness by the simple thin-walled cylinder model with sigma equal 7,000 psi subjected internal pressure which equal to the pressure rating class designation number PC for class 150 to class 2500. It is estimated that for class 4500 the calculated wall thickness TB by the equation B1 is 1.37 times as large as the calculated thickness by the Lamé's stress equation. The equation for the working pressure PSP of pressure temperature ratings for special class equation B4, assuming that 70,000 psi of the tensile strength of WCB casting is considered as the basic strength in ASME B16.34. PSP equal 70,000 multiply 0.25 divided by 7,000 multiply PR. So we obtain the PSP equal 2.5 multiply PR. So PSP equal CWP of the sailing pressure in table B, I13C. Comparison equation based on simple thin-walled cylinder model between T dash number 1 equation derived from B1 and TP equation number 2 for piping component. In case of the following factors are as follows: SF 7,000 constant stress. So S is the allowable stress. PC is the pressure rating class number. P is the internal pressure of called working pressure of the special class sailing pressure. Assuming that the tensile strength 70,000 psi of WCB casting is considered as the basic strength in ASME B16.34. Allowable stress is S equal 70,000 psi multiply 25% equal 70,500 psi in estimation of casting quality factor equal 1.0. We understand that T dash by valve wall thickness equation 1 equals to TP by piping component wall thickness equation as shown B in the Dutch table for 1 to 2. For 1 to 2. So this table indicated tabularized So the valve wall thickness calculation and the piping wall component is calculation thickness. So PC is a pressure rating class 115, 306 like this, and the SF is a best constant, stress-based constant 7,000 like this. So substitute the PC and D like this value and calculate the wall thickness for valve component T dash equal 0.008 multiply D inside diameter. We obtain the like this thickness. And here for piping component, assuming the WCB casting. So cold working pressure, sealing pressure, so 290, 750. So and also allowable stress S 70,000 psi multiply 0.25. So number 2, the casting quality factor equal 1.0 estimated. So substitute these numbers to assign into the P and S. So calculate the TP thickness like this obtained. So compare the T dash and the TP, the same values obtained. This is very equal. So we understand that T dash by valve wall thickness equation 1 equals to TP by piping component wall thickness equation as shown B in the attached table 4.1.2.2. Now we talk about the comparison with the equation of wall thickness of valve, pressure vessel, and pipe. So again, I assign the wall thickness equation for valve, equation B1. So wall thickness equation for the pressure vessel in ASME section 8 division 1. So T equal P multiply D bar 2 parenthesis sigma A multiply eta minus 0.6 multiply P in parenthesis, where P internal design pressure, D is the inside diameter, sigma A maximum allowable strength, and eta is the welding joint efficiency. So again also wall thickness equation for the pipe in ASME B31.1 assigned. So that this wall thickness assigned is based on the outside diameter equation. So like this. So P equal internal design pressure, DO outside diameter, and the denominator, so S the maximum allowable strength, E joint efficiency if we use the casting pipe, so assign the F. And W, the weld strength reduction factor. And also Y. Y is introduced in the ASME B31.1 coefficient having values as given in table 104.1.2-1. So convert the equation based on outside diameter into the inside diameter basis. So wall thickness for pipe component ASME B31.1 is calculated on the basis of the outside diameter. This equation converts the basis of outside diameter into inside diameter to compare to the other equation with the basis of inside diameter. This conversion equation is we talked about just before, so that this is basis of earth diameter DO in ASME B31.1 to convert to the T equal PD is so the basis of inside diameter D in ASME B31.1. So comparison with the equation of wall thickness of valves, pressure vessel, and piping component into unified inside diameter D, assuming no welding joint on the longitudinal area in the pressure retaining part. So welding joint efficiency eta equal 1.0, also E equal 1.0, and casting quality factor F equal 1.0, W equal 1.0. So three wall thickness calculation equation is aligned here. So first equation is for valve ASME B16.34 valve. Second, T equal P like this number. So ASME section 8 division 1 for pressure vessel. Third equation is for piping component for ASME B31.1. So look at three equations. We think very same equation with the three equations. It is supposed that the above three equations are basically same and modified from the equation by the simple thin-walled cylinder model. So from now, we will discuss what is the original equation for the current wall thickness equation about the pressure retaining parts. So first, we talk about the stress analysis of thin-walled internally pressurized cylindrical vessel. So when the cylindrical vessel is subject to an internal pressure, the stress occurs through the thickness. Its actual stress occurred will vary with higher on the internal diameter side and lower on the outside diameter side. This is typically the thick-walled pressure vessel. So apply the internal pressure P. So the stress occurred on the thickness. So the produced stress is not even. So something distributed like this manner. So inside the maximum stress produces the inside diameter point, and reduce the stress to the outside surface. So that the stress is distributed like this. So it is said that for the thin-walled assumption to be valid, the vessel must have a wall thickness of no more than about 1/10 of the vessel radius. So it is said that the thin-walled cylinder vessel has the stress is very even stress produced in the thickness through the thickness area. So we something consider about the wall calculation. The thin walled pressure vessels to be considered. So the vessel must have a wall thickness of no more than about 1/10 of the vessel radius. But in case of the standard such as ASME section 8 division 1, thin-walled cylindrical vessel is considered if the thickness is less than 1/4 for the vessel in the diameter. So T less than 1/4 in the diameter. So relate the equation K equal d/d introduces. So K less than 1.5 less than is almost all standard admit the thin wall thickness cylinder. So here the figure, this is a thicker wall thickness, so that wall stress is distributed some changing, but thin wall thickness cylinder produce the stress is evenly, very constant. So that definition is T less than d/4 is a constant stress assumption distributed on the cross-sectional area. So even the stress produced in a thin-walled thickness cylinder. Consider the simple thin-walled internally pressurized cylinder model, which has inside diameter d, here d, and thickness t, and the length L. If it is subject to the internal pressure P, the cylinder has two different stress values of circumferential stress, or we call Fob stress, which act in the direction of the cylindrical tangential Fob stress. And also, one stress is a longitudinal stress, which acts in the direction of the cylinder axis. So stress is like this here, longitudinal stress act. So if the inside pressure applied, the vessel is two different stress produced. So now we are analyzing the stress analysis of thin-walled internally pressurized cylinder vessel. So number one, introduce of circumferential stress, foot stress on the simple thin-walled cylinder model. So when tensile force in the vertical direction is F1, which is produced by under internal pressure. So internal pressure P applied in the vessel. So F1, so vertical up and down side direction, the force is produced. So this F1 produces over force. So the cylinder pressurized cylinder is burst. So where is that burst? The longitudinal area is bursting. That the thickness area is breakage apart from the up and down. So this is breakage here. So tangential stress like this. So F1 force is applied. So F1 is indicated for internal pressure multiply inside sectional area in axis direction. So pressure receiving surface here, like this here. So that area is inside the diameter D multiply length L. This pressure received surface. So internal pressure P multiply inside diameter D multiply length L. This is produced F1. The occurred tensile force is indicated as F1 divided by wall thickness area in axis direction. This is a stress in produce the wall thickness area. So force divided by the sectional area of the wall thickness area. So wall thickness area is thickness T and multiply L and 2 points. So the denominator 2 multiply T thickness T multiply length L 2 points. So multiply 2 multiply. So the simplifies the equation P multiply D bar 2 multiply T. So sigma 1 equal PD bar to T. This is a famous equation, circumferential stress or foot stress, so called. Number 2, introduce of longitudinal stress on the simple thin-walled cylinder model. When tensile force in the axis direction is F2, so this, so axial direction like this. So breakage F2 is over force. So vessel is breakage here, tear from here. So for F2 force equal internal pressure multiply. So this is a pressure receiving surface area here. So inside the cross-sectional area, so pi multiply d square bar 4. So multiply P, internal pressure. This is a produce F2 force. The occurred tensile stress is indicated as F2 divided by wall thickness area. Wall thickness area like here. So thickness T and circumferential length multiply that. So this is thickness area. So this denominator produce stress. So simplify the equations. P bar P multiply D bar for multiply T. So sigma 2 equal PD bar for T. This is a longitudinal stress. Which stress is bigger than that? The sigma 1 or sigma 2? So comparison of circumferential stress. Hoop stress sigma 1 equal PD bar 2T and longitudinal stress sigma 2 equal PD bar 4T. So sigma 1 to sigma 2 equal 2 to 1. So sigma 1 is circumferential stress is always usually bigger than longitudinal stress. Sigma 1 of circumferential stress, hoop stress, is usually larger than longitudinal stress. When the cylinder is subject to internal overpressure, breakage is normally occurred along the axis direction. So breakage, overpressure breakage, so that like this breakage here. Then not possible the breakage like here. Always breakage like this breakage here for overpressurized. The sigma 1 of circumferential stress, hoop stress, must be considered on the required wall thickness of the pressurized cylinder. So next, we discuss about the circumferential stress, hoop stress, sigma equal PD bar 2T, which is introduced by simple thin walled cylinder design model, be actually applied to calculation of the required wall thickness. So this is my simple question. Before. So the data of comparison between the circumferential stress and actual burst test was found on the article. I found some articles, the figure like this. So horizontal line indicated K equal D over DI. This index is K ratio. And the vertical line indicated PB bar sigma B. PB equal burst, actual burst pressure data, and denominator sigma b is tensile stress. Tensile stress strength is mean breakage strength. The plotted data attached in the right side here. Vertical axis indicated the rate of burst pressure PB and tensile strength sigma B, or PB by sigma B. Horizontal axis indicates the rate of outside diameter dO and inside diameter di, or K equal d0 by di. The plot of circle in the figure circle plot. This N indicated the actual burst test data. So this dot line indicated the basic equation, source equation, sigma 1 equal PD bar 2T. PD bar 2T, circumferential stress, P sigma 1 equal PD bar 2T. So, drawing the line here. So, compare the actual test data. The sigma 1 equal PD by 2T. So in case of the K equal 1.5, so that intersection point is 0.5, the PB by sigma B, 0.5, this equation. So that, but actual test data, burst data around the PB by sigma B is around 0.42. So 0.42, in case of the 0.42, actually actual test is burst. But calculation of the sigma 1 equal PD by 2T is relatively high pressure to be burst. This is a very critical point. This is a very dangerous point because of the this equation calculated wall thickness. So the burst point is a very dangerous point is indicated. So must be the calculation data is lower than test data. Lower here. So this means that the estimations by using of sigma 1 equal PD by 2T indicate higher burst pressure than actual burst pressure and are more at risk. Sigma 1 equal PD by 2T cannot be used for the wall thickness calculation as it is. So next is the attempt to find the practical wall thickness calculation equation in the pressure vessel. To find out how the practical wall thickness calculation equation was established. So inside diameter D is a very critical number. Inside diameter D need to be considered. D shall be taken as mean diameter initially, or D tend to increase when the vessel is pressurized and associate with the expansion. Normal thinking, if the pressure applied the vessel, so vessel is pressurized and expansion. Expansion is mean inside diameter d increasing. So after pressurized, over pressurized, finally the vessel is breakage. At that time, the breakage point is d is something increasing the original inside diameter d. So inside diameter d is something increasing. This is something consideration. So d shall be taken as mean diameter initially, or d tend to increase when the vessel is pressurized and associated with the expansion. So following modified equation of the circumferential stress is considered with modification as adoption of virtual diameter about increase of the inside diameter d with introduce of correction factor beta. So sigma 1 equal PD by 2T. This is the basic stress equation. As modified to sigma 1 equal P multiply. So D inside diameter D increasing plus to beta T. Beta introduce the correction factor T. And like this. So when beta equal 0.5, term of d plus 2 beta t is shown as mean diameter. So beta equal 0.6, 0.5, so mean diameter indicated virtually d. So beta equal 1.0, increasing the d and to the outside diameter indicated. So beta equals 0 is indicated the originally inside diameter d. So when beta equals 0.5, term of d plus 2 beta t is shown as mean diameter. When beta equals 1.0, term of d plus 2 beta t is shown as outside diameter. So now we will discuss about the confirm the modified wall thickness equation with the introduce of the correction factor beta. So newly assign the modified equation sigma 1 equal p parenthesis d plus 2 beta t parenthesis bar 2t. The attached figure shows comparison between the result diagrams with substitution of the value of 0.1, 0.2, 0.3, etc. into the factor beta in the modified equation and the burst test data. This figure, this chart is the same as the like this figure data. So I plotted the test of data, circle data is here. So this dot line the burst test data the indicated here. And horizontal axis and vertical axis the same manner of the just before figure from article figure. So blue line indicates originally the based on stress sickness stress equation, sigma 1 equal PD bar 2T in this line. So K equal 1.5. So indicated 0.5 for the P bar sigma 1. P is the burst pressure. Sigma 1 equals the tensile strength. So in case of the beta, so the 0.1, 0.2, 0.3, 0.4, changing the beta and draw the line here. So beta equals 0.1 indicates the drawn line here like this. So beta equals 0.1 is still higher position with the burst test data. So beta equal 0.1, so we cannot use the beta equal 0.1. So 0.2 something lower point, but still higher than burst test data. So beta equals 0.3 also higher than test data. So beta equals 0.4 higher, beta equals 0.5. So beta equals 0.6 is something good because of the test data, the red line indicated lower than burst test data, and also very close to the burst test data. So if the beta equals 0.8, 0.9 is a lower position, but this is a very safety position. Safety position is mean calculated wall thickness very thick condition. So we have to select the wall thickness calculation equation is the actual test data is very close and not so much apart, very close, and the lower position indicated. So I think equation beta equals 0.2 is a very good condition, I think. This comparison shows the diagram of equation beta equals 0.6 is very close to the burst test data and located in the lower area. This means that the modified wall thickness equation of adoption of beta equals 0.6 has a practical use and advantage in terms of safety. Rewrite the modified equation of sigma 1 to the equation of T. So this is a stress equation. So convert to the wall thickness equation like this. Convert to the wall thickness equation. So beta equals 0.6 substitute. Here 0.6 substitute. It is understood that the wall thickness equation, which was adopted to beta equals 0.6, was introduced in the standard of ASME Section 8, Division 1 or ASME B31.1. We obtained the wall thickness T calculation in beta equals 0.6. So compare This equation is section 8 division 1 for pressure vessel. It is very matching this equation. Also, piping wall thickness calculation equation like the same. Also, valve equation same. So from this figure, uh, uh, we understood beta equal 0.6 is something very close and correct equations, as we think. So now we have to confidence. So comparison between the Lamé's stress equation and the modified stress equation based on thin-walled cylinder. Again, looking at the comparison charts between the balance test data here again and several stress equations which are shown a moment ago, it is understood the diagram of the Lamé stress equation is very close to the burst test data, and also it is reasonable equation for the wall thickness calculation. So that this is the Lamé's equation line here. This is very close to the burst data and the lower portion indicated. So the Lamé's equation is very good equation for the wall thickness calculation. So fails us as actual test data. So essentially, Lamé's stress equation is used to calculate the wall thickness regardless of thickness of pressure vessel due to its validity is recognized. Also, this is a validity recognized. Actually, the modified stress equation, which is adopted to beta equals 0.6, was based on thin-walled vessel, become widely available in many standards. The standard apply K equal D0 bar Di equal 1.5 to distinguish between thin-walled vessel and thick-walled vessel. Lamé's stress equation will be used for thick-walled cylinder. So this is a K equal 1.5 line. So reduce the K number, K rate indicated a thin-walled cylinder. K equal 1.5 larger area is a thick-walled cylinder. So Lamé's stress equation is expressed the following as circumferential stress, hoop stress, put sigma 1, sigma 1 equal P parenthesis 1 plus like this, so denominator like this. So here A inner radius, B outer radius, R is the arbitrary radius. It is said that maximum stress is occurred on the inside diameter and minimum stress is occurred on the outer surface in the pressurized cylinder. Again, we look at the cylinder here. So pressurized cylinder, maximum stress produce the inside diameter, and minimum the outside diameter. So maximum stress, the sigma 1 maximum, the where arbitrary R equal A equals the inside diameter, inner radius. So like the sigma 1 maximum, like this equation. So minimum stress, sigma 1 minimum, the where R equal B equals the outer radius, so outside diameter area, so B. So substitute the B, so delete it and simplify the equation. Sigma 1 minimum to P bar parenthesis B bar A square minus 1 parenthesis. This is a simplified equation. But we usually consider about the maximum stress equation like this for wall thickness calculation. So modified stress equation developed from the thin-walled cylinder model and adapted to correction factor beta is follows like this, and rewrite the following equation with T equal to A. So this is the inside diameter. So the inner radius A, rewriting the sigma 1 equal like this. Simplify the equation. P parenthesis A plus beta T parenthesis bar T. Accordance with the standard. The cylinders with wall thickness less than K equal 1.5 are considered thin-walled cylinder, and the modified stress equation, which is developed from thin-walled cylinder model, can be used for the required thickness calculation on it. K equal B bar A. B the outer radius, A equal inner radius, so 1.5. To distinguish between thin-walled cylinder and thick-walled cylinder. In case of K equal 1.5, it is assumed that the calculated stress by Lamé stress equation and the calculated stress by the modified thin-walled stress equation match the same. So at that point K 1.5, K equal 1.5, so Lamé's stress equation and modified stress equation is the same. So the Lamé's equation, stress equation, and the thin-walled simple equation, modified equation here equal. So because of K equal MB, so delete the P and B bar A equal 1.5. So substitute the 1.5 and sums. So the simplify the equation 2.6 equal match parentheses A plus beta T parentheses bar T. So T equal B minus A. B equal outer radius, A equal inner radius. So B minus A equal thickness T. So thickness T equal B equal 1.5A. minus A. So T equal 0.5A. So substitute T equal 0.5A. So here 0.5A assigned. So outer radius deleted, A deleted. So simplify the equation. Also, result in beta equal 0.6 is obtained. So this is confidence. I have confidence of the beta equal 0.6 is correct for the wall thickness calculation. So again, next table shows the comparison between balanced stress equation and the modified stress equation based on the thin-walled cylinder model against the rate of K equal outer radius bar inner radius. It is understood that the modified stress equation with beta equal 0.6 matches the Lamé stress equation under the condition K 1.5 less than 1.5. So that equation is confidence of the K equal 1.5, but less than 1.5, we have to confirm the beta equal 0.6. So this table is a comparison stress sigma 1 P between Lamé's stress equation and modified stress equation based on thin-walled cylinder. So the maximum stress equation of Lamé, this is Lamé's maximum stress equation. So lower area is a modified stress equation based on thin-walled cylinder. So this is a modified stress equation based on the thin-walled cylinder introduced with the correction factor beta. So beta equal 1.0. So and beta equal 0.9 like this number, like this equation. Beta equal 0.8. So beta 0.5, 0.56 like this. So horizontal is K equal B by A. Okay, so 1.1, 1.2, 1.3, 1.4, something. So sigma 1 maximum P, this stress ratio calculated. So sigma 1 maximum divided by P. Sigma 1 divided by P. Calculate the number like this. So we compare the Lamé's stress value 10.52, 5.553. This value is to be compared some other beta which beta is correct or something. So we compare the value. So beta equals 0.6. The data, calculated data value is almost same as the Lamé's equations. Here. After K equal 1.5 more, something different in the value. produce. So I understand the beta equal 0.6 is I have a confidence below the k equal 1.5. So with the Lamé's stress equation matching. So it is understood that the modified stress equation with beta equal 0.6 match the Lamé's stress equation under the condition of k less than 1.5. So comparison between the stress equation based on inside diameter d standard and the stress equation based on outside diameter DO standard. Inside diameter standard, sigma y equal T parentheses D plus 2 beta T parentheses bar 2T convert to the outside diameter standard. Sigma y equal P parentheses D0 bar 2T bar minus bar 1 minus beta like this. So in case of beta equal 0.6, so beta 0.6 inside diameter standard, sigma 1 equal P parentheses D plus 1.2 T parentheses bar 2T. So convert into the wall thickness equation T equal PD bar like this equation. This is very much for the ASME section 8 division 1 equation. So introduced in ASME section 8 division 1. Outside diameter standard sigma 1 is beta equal 0.6. So convert into the wall thickness equation T, this stress equation, and the thickness equation convert to like this. So 0.4 P, 0.4. This is introduced in ASME B31.1 below and 900 Fahrenheit. So y equal 0.4 below and 900 Fahrenheit. So 900 Fahrenheit temperature or more over temperature, Y factor is something different, changing and increasing the number. So I will talk about the Y factor something with the next video. I will talk about. So today is all I have for today. So that's all I have today. I will talk about the equation of wall thickness calculation for ASME B31.1 and temperature dependency for parameter Y with the next video number 5. Thank you very much for watching.